Can anyone give me an idea like why we are talking about this now? Why we are talking about Newton-Raphson now? So this is similar to root finding, okay? So, but our goal is one thing. What is our goal? Our goal is, our goal is to find x star. Find x star such that x star equals to R min of fx. And x belongs to any space x. Yes. Can you just think how root finding is, like how Newton-Raphson can help us solve this optimization problem? Any ideas? How root finding can help us in finding this? Maybe okay. So let us look into this problem geometrically. Like as we did in the previous semester for Newton-Raphson, same thing we will do here. Suppose you have this function over here. Function fx. This is y equals to f of x. This is y. This is x. Fine. This is y. This is x. Okay. My job is to find what value of x fx is minimized. What should be the value of x? From this figure, which value of x minimizes the function? Value of x minimizes the figure. Middle. No, somewhere like here, 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 somewhere there. But somewhere out of these points. Okay, where? That is our job. Where? That is our job. Okay. Okay, fine. So as usual, what we should go? What we should do in any numerical method? What's our first step? Yes, take an initial guess. Okay. So start with an initial guess. Start with an initial guess. Start with an initial guess. Say x naught. Okay, maybe yeah. Maybe I would prefer writing on the top. That's the first point. So x naught where we can take, can anyone give you an idea? Like x naught may be this point. This is x naught. Okay, what we do next? Hmm? Yes, exactly. Take the derivative at that point, like the tangent, and see where it intersects. Take the tangent at that point and see where it intersects. It intersects here. Okay, it intersected here. That will be our new point. That will be our new point. Okay. Then check the value of the function at that point. Is it minimum? Is it minimum? If not, carry out the iteration till minimum is reached. That's the idea. That's the idea of Newton-Raphson method. Okay. Okay, so we'll do it in a more good way. Fine. I will tell you in a different perspective. I will give you a different perspective of this idea. Okay, this problem. Suppose you are here. This is our starting point x naught. The slope is positive, isn't it? Slope is positive. You can see that. What does it mean for the slope to be positive? If the slope is positive, it means if you go to the right of that point, function will increase. How many of you understood this? Mr. Aditya? Take the point, take a random initial guess. That is x0. Take the slope. What is the slope at that point? You don't know, but it is positive. That you know. Slope is positive. If the slope is positive, what it means? Function is increasing. If the slope is positive, that means rate of change of function is increasing. So if you go to the right, okay, the function will increase. That as x increase, function increase. So as you go to the right, as you go this side, f increases. For x naught, I am saying. For x naught to be the starting point. But our goal is it to maximize fx? Is a maximize fx? Minimize fx. So where should we go? Should go to the left. Can you see now? Logic behind this method, how it should work. Take an initial guess, see the slope. If the slope is positive, move left. Understood, right? If the slope is positive, slope is positive, or f prime x is greater than 0, move left. Okay, now let us come to a very nice other case. Point. This tangent. What's the value of f prime x? Negative. It makes angle with the x-axis. So f prime x is negative. If f prime x is negative, what it means? Move towards. Yes. So where we should move? Slow. So if f prime x is less than 0, move right. To attain minimization. Why we are all doing this? To attain minimum of fx. Okay, so depending on the sign of f prime x, we have to move left or we have to move right in order to reach the optimal solution. That is the basic idea of Newton-Raphson method. Okay, fine. So therefore, to mathematically capture this idea and write as some notation, we will use two different variables here. Okay, one is known as d naught. What is d naught? This indicates, this d naught indicates the descent direction, where you want to go, the descent direction, whether to the left or to the right. Now you can get an idea of why gradient descent is referred to as gradient descent. Okay, so descent means you are going somewhere to attain that solution. Okay, so Newton-Raphson is also using the same descent method, similar descent method. Okay, so descent means where you have to go, whether to the left or to the right. Now can I ask you, is that sufficient? Like, is the information going to the left and going to the right sufficient, or you need some more information? Is there any other information needed? Yes, exactly. How much you have to go? How much you have to go? If you are a gorilla, okay, you will go bigger steps. Okay, but you will, so therefore gorillas miss out laddus, isn't it? If you put laddu, gorilla will miss because he might not be able to see. He will go a lot more step. But if you are small, okay, then you can find the goal. Yes. So therefore, how much step you have to go? That's important. How much step you have to go to the left? How much step you have to go to the right? So therefore, this motivates me to introduce another parameter, that is h naught, okay, which indicates the step size. Step size. How much d naught will give me the direction where I have to go, whether to the right or to the left, and h naught will give me the direction how much I can go to the right or left. How much amount? H naught. That is the step size. Okay, fine. Okay. So now I will write very formally, if f prime x at x equal to x0, as the starting point is greater than 0, then fx increases with x. Fx increases as we increase x, isn't it? So increase x, okay. So then the descent direction, should be, where? Should be left, means Left means, no, left means it should be less than x0. So it means the new point, that is x1, the new iteration should be less than x0. Isn't it? Left of x0. Got that idea? Okay. Now, if f prime at x equals to x0, okay, is less than 0, that means fx decreases with increase in x. Okay. So the descent direction should be, then the descent direction should be, anyone? Where it should be? Should be, this is left and this is right. Should be towards the right. That is x1 should be greater than x0. Isn't it? Got that idea? Okay. So therefore, what can we say? Can we write what should be the descent direction? What should be the descent direction? So you can see if f prime, if we say right to be positive, usually right is considered to be positive, notation wise, left is considered to be negative. If f prime is positive, d naught is negative. Okay, so it's opposite side. So the best candidate is consider d to be negative of f prime x equals to x0. This is the best candidate. Consider d to be negative of the derivative at the initial guess. Fine. Okay. So this is how the method will go now. Wait. It's, okay. So now what was our job? Like we started with an initial guess, and now we know where we should go depending on the sign of f prime x. So we have to, our job is now to write what is our next iterate should be. What should be x1? That is our now new step. Okay, fine. So let us bring that here so that you can see the new things. So consider the initial guess. We started with an initial guess x0. X0 is the initial guess. Okay. Okay. What should be our new point? That is x1. X1 should be the initial guess, that is x0 plus where you have to go and how much you have to go. Where you have to go and how much you have to go. That is being captured by h0 times d0. h0 will tell you how much to go, d0 will tell you in which direction. So x1 equals to x0 plus h0 d0. Got that idea? Okay, fine. So d0, as I told you, is the descent direction or travel direction. Here d0 is considered to be negative of f prime. Fine. This is the story so far. But the story is not yet over. Our aim is not to do this. Our aim is to minimize effects. Our aim is to minimize effects. Therefore, we started with this Newton-Raphson. How we can minimize effects. Okay, so our job is to find which direction is true. Direction is true, but step size is not yet fixed. We said h0, but we did not quantify. We did not quantify the step size h0. How much h0 should be? That we did not calculate yet. So we want to calculate the step size h0 is how much, which minimizes f of x. Which minimizes f of x. That means, suppose it minimizes f of x in the next iteration. Suppose it minimizes f of x in the first iteration. What does it mean? F prime at x equals to x1 should be 0. If the derivative is 0, you have reached a minimum. Of course, we have not checked the second derivative, but this is it can be either minimum or maximum. We'll check. But this should be satisfied, right? F prime at x equal to x1 should be 0. Now, what is x1? X1 is this. Can we substitute inside? X1 is x0 plus h0 d0 equal to 0. Yeah. What this tells you? Can you do something here? Can you expand in some way? Does this remind you of something? Does this remind you of f of x plus h? Does this remind you Taylor series? Does this remind you of Taylor series? I hope it reminds you of Taylor series. Okay, you can always expand this function here. Okay, in terms of f prime x. So this you can write this approximately f prime x naught plus h naught d naught f double prime of x naught and so on, order 3 numbers. Okay, that is equal to 0. Order 3 you can neglect it, but maybe this one we will neglect. There is no small, we will encounter an error of degree 3. But can you see that something is going to happen here? Can you see that we are able to get h naught from this? What should be h naught? What should be h naught? H naught equal to f dash of divided by good. That's what I was wondering. You might miss. So h naught is negative of this. Okay, agreed. So far agreed. But d naught was something, right? You only told me that d naught is minus of f prime. D naught is minus of f prime. So can we simplify it more? Minus f prime at x0 divided by d naught is again minus of f prime at x0 multiplied by f double prime at x0. So this are cancelling out. So you just got 1 by f double prime at x0. Agreed? Agreed. So can we write down again the new this one? Can we replace? So what our job was to find what is this value, what is this value? Nothing else. Can we put them back in equation 1? Put them back in. Put them back in equation 1. So what are you getting? x1 equals to x0 plus h0 is 1 by f double prime x0. What is d naught? Yes, minus f prime x0. Can we write it a better way? x1 equals to x0 plus, sorry, minus of f prime at x0 divided by f double prime at x0. Sorry. Is it okay? Or something wrong is there? It's okay. You see something happening here. Like, yeah, you can in general write this. In general, maybe it would be good for me to write this. In general, this is x1, x0. In general, you can just write it as xk plus 1 is equal to xk minus f prime at xk divided by f double prime at xk. If you go to the next step, x2 you calculate similarly. It will be again x3. If you do, it will again depend on x2. So that you can do it, but in general, you can write like this. Does it remind you of something in previous semester? What it reminds you? That, yes. So here you are doing, previously in previous semester you did Newton-Raphson. Previous semester, you applied Newton-Raphson to compute root of fx, compute root of f of x equal to 0. Current semester, you are applying Newton-Raphson to compute root of f prime x equal to 0. Can you see this happening? If you consider that f to be f prime, then that f prime is at the top and that derivative is at the bottom. So you are doing nothing but applying Newton-Raphson to the derivative of that function. Okay. And especially you want to find what value of x is giving you f prime x equal to 0, which you already know that will give you minimum. So you're applying Newton-Raphson to this, nothing else. But you can see how nice logics are framed inside this method, like where to go, how to go, the descent and all are incorporated within this method. So I hope you can appreciate. I could have told you just this one, but I started with a method of descent so that in your mind you can actually intuitively understand which direction you should go to minimize the function. Okay, so that this serves as a basis of the gradient descent. This method serves as a basis for gradient descent, and we will try to what is it? But we are having fun with Newton-Raphson method. But what is the demerit of Newton-Raphson? Yeah, the last time also there was a demerit of Newton-Raphson. What is the demerit of this Newton-Raphson? Yes, exactly. We need our function f to be second order differentiable, like twice differentiable. Not many functions we saw, mod x and all are not twice differentiable. So for those functions, you cannot apply Newton-Raphson. For those functions, you cannot apply. You can only apply Newton-Raphson to those functions which have the derivative. Okay. So now you know where, like, So this is this methodology is a general procedure for gradient-based optimization, which is also applicable to multidimensional case. You can generalize this multidimensional cases. Multidimensional cases like where you will see that instead of f prime, you can use gradient. Instead of f double prime, you can use the Hessian. Okay, that's the basis of gradient descent, which we will be covering in the next 2 or 3 classes. Okay, that will be our saga, like of gradient descent, stochastic gradient descent, mini batch gradient descent, Adam optimizer. Everything will follow this. So I suggest everyone to read up to what I have taught in the class, line by line, bit by bit. If you to understand the next classes. Okay, fine. So what I will do is we will do one example here. Okay, a simple example just to appreciate the method. Then I can maybe give you one example for homework assignment. Okay, which will be due maybe on 17th February. Fine. Compute the value of root 2. Okay, maybe no. No, not that way. We'll frame the question. Okay, minimize f of x equals to x square minus 2. Okay, minimize this fx. F of x is x square minus 2. Okay, use the Raphson method. So what we need? You need an initial guess. You think what should be the initial guess? You take, up to you. Okay, take the initial guess. Take the initial guess. Then this is x naught and make a table. X naught and then f prime at x0, f double prime at x0. What are the values? Okay, make a table, and this will give you an idea what should be x1. Okay, what should be x1? You know already from the previous case that you can compute k plus 1 like this. So let you do some few iterations and let me know where your x is converging to. That will be the optimized solution or optimal solution to this fx. Okay, start. Yeah. So yeah, this is the assignment, and function fx which has a different derivative. If it doesn't have a derivative, you cannot do anything on Newton-Raphson. So yeah, like Newton-Raphson method is fast, it is accurate, but it requires good initial guess in order to converge to the root of f prime x. So yeah, Newton-Raphson method is a gradient-based method, especially because you see you are computing derivative and double derivative. Okay, so it depends on the descent direction also, where you have to go to approach to the minimum. Fine. So, but there are some methods which are much more better than Newton method, which is known as quasi-Newton method. Okay, quasi-Newton method. This is much better than, this is better than Newton-Raphson, better than Newton-Raphson method, better than Newton-Raphson method above. It is almost similar to Newton-Raphson, but there will be like some difference in the Newton-Raphson method, which makes it a new method known as quasi-Newton method. All right, and as usual, it avoids the drawbacks of Newton-Raphson. It avoids the drawback of Newton-Raphson. Maybe we can cover this in the next class. New drawback of NR. So this is the first method we learned, Newton-Raphson. Next few classes we'll be learning more such methods. Okay, with that we can stop.